this notion of an iterative algorithm is really valuable. It broadens dramatically the class of things that we can compute. Again, if I just have branching things, I can only go through the code once. Now I can start generalizing. And so we've got things that do much more than just the simple arithmetic we were doing earlier. We can repeat a sequence of steps multiple times based on a decision. One of the things that comes out naturally once we have this idea of repeating things is a set of methods that are sometimes called guess and check methods. They're very useful, even though they're not always the most efficient technique. And I want to extend that notion of iterative algorithms to capture examples of guess and check methods. Go back to what we talked about in an earlier lecture. Remember we had that declarative definition of square root. Square root of x was that y such that y squared was equal to x. And I said, if we were lucky somebody gave us a guess, we could at least use it to check whether we were right. Now we went and looked a different direction. We looked at an algorithm to actually compute it. But we can go back to that idea. Because if we had a good way to generate guesses, we could use that declarative definition to check. That's the basis of guess and check. I'm going to have to come up with a way of systematically making guesses for the possible answer, check them, and keep doing that in an iterative algorithm until I find a good solution. Let's see how we might do that. I'm going to use cube root rather than square root just to change it up a little bit, but the same idea would work. One way to use this idea would be to try and find, for example, starting at 0, try 0 cubed, then 1 cubed, then 2 cubed, and so on until I get to a point where I find a k such that k cubed is greater than x. If I found the cube root before then, I stop, but once I've got something greater than x, I know I can stop. Now clearly this is only going to work for integers. I can't do it for all possible numbers, but in this case there's only a finite number of things that I need to try. So let's see what that would do. Here's some code that would actually make it happen. I'm going to start by inputting an integer. Notice my use of input. I'll remind you that says it's going to print out that message, then read in whatever I type in into the environment inside Python. Remember that input returns something as a string, so I'm going to convert it into an integer. It's going to assume I typed in an integer. If I give it something else, it's not going to work. And then I'm just going to have a little loop. I'm going to set up answer to be 0. And then, as long as I have something that's less than the thing I'm trying to find the cube of, I'm just going to increment, add 1 to it. And I'm going to keep doing that until I get something that is something where the cube is either equal to x or greater than x. And once I get there, I'll simply check to see, did I actually get the cube by doing a test. Let's try this out. Again, I've got a little same piece of code over here. I'm going to load it into my system. It says enter an integer. Let's give it something reasonable like 27. So in my environment, I give it 27. Oh, good. Cube root is, in fact, 3. Let's try something else. Again, I'm going to load this into my system. And I don't know, let's pick 38. And it says, doesn't work. It's not a perfect cube. All right, my code runs. What was this doing? It's simply using a loop right here to generate guesses. And it's going to keep doing that until it gets either to something that is the right thing or has gone too far, in which case I'm simply going to do a check to see which case I'm in. Here I'm using that declarative knowledge because there's the test. The test is right there to see, do I have something that is in fact the cube root? That's nice. That's what I'd like. What could I say about this piece of code? Well, first of all, it's only going to work for positive integers. Okay, I could easily fix that by just keeping track of the sign and then looking at the solution to the positive case. And I do this because one of the things we want to do with code is think about how well does it run? Does it run on all the things I expected? And how might I modify it? And here the modification is actually pretty straightforward. I'm going to do the same kind of thing. I'm going to run the code, but I'm going to use abs, which is a built-in function, to take the absolute value of x. I'm going to check the cube root against the absolute value of x. And then when I'm done, I can just decide down here whether in fact I want the negative or positive version of that. I could make that change and run it. I'm not going to do it. It'll work for me, but it simply shows you that I can easily extend my code to build new versions of things to handle cases that I didn't think about when I wrote the first version of the code. There's the first version of a guess and check method. A little slow, but it does the right kind of thing. Now, one of the things that we've talked about is that we know when we do a loop that we need some characteristics. In particular, we need a loop variable that's initialized outside the loop, that changes within the loop, and that's used to test when I'm done. That notion we can also capture in a little bit more general form, because it's useful to think about what's happening inside the loop. How do I know the loop's actually going to stop? And for that, we often want to think about something we call a decrementing function. The idea is that we're going to map all of the program variables into an integer, and when the loop is entered, that value is going to be something that's non-negative. When I go through the loop, it's going to keep decreasing, and when that value gets less than or equal to 0, I know I want to terminate. So this is a capturing of this idea of the loop variable in terms of looking at what's being done inside the loop. And in my case here, I was simply using the absolute value of x minus answer cubed as my decrementing function. If you think about it, every time through the loop, that is decreasing. And once it gets to a stage where it's either less than or equal to 0, I'm ready to stop, and I'm going to be able to go on to see whether I've actually computed a perfect cube or not. What could go wrong? Well, these are the standard problems with a loop. Suppose I don't initialize the variable. Most likely thing is I get something called a name error, which is I'm going to try and refer inside the loop to something that I haven't defined outside the loop. There is no value. I can't look it up. That's at least okay. I'm going to stop. What's worse is if I've used that loop variable somewhere else in my code before this, I'm actually going to get something that starts up the computation in a place I don't expect. And that's a harder problem to find. So this is one of the things we always want to remember with loops. Make sure we initialize the variable before we start it. What if I forget to change the variable inside the loop? I'm in trouble, because I'm going to go through that loop until I get really tired of the machine running. It's going to simply go through what we call an infinite loop, doing exactly the same code over and over and over again, because it will never reach a terminating condition. And those are two standard problems with using a loop. A while loop in particular is I've got to make sure I set up the variable ahead of time, I've got to make sure I'm changing it inside the loop, and I need to make sure that the termination test is actually using that variable appropriately. But as long as I get into the discipline of that, set the variable, write the loop, decrement the variable inside the loop, and check for it, I should be okay. So that gives us actually a broad class of algorithms. Not the most efficient, not going to work in every case, but a good guess and check algorithm is something where you guess a value, you check to see if it's right, you change the conditions inside the loop, and you keep guessing until you find a solution or you've used up all the possible values. This is an example of a set of algorithms called exhaustive enumeration. And you can see why exhaustive. Two reasons. One, you're going to exhaust all possible options to use. And two is it's going to take a while to run, so you get tired waiting for it to finish. But as computers get faster, surprisingly many of these algorithms can actually work quite well. On the other hand, I might not want to always think about making sure I initialize a loop variable, do a while loop, and then change it inside. So I could clean this code up by using the other kind of iteration structure, a for loop. So here's a nice variation of that. I could set up a value for cube. I could have read it in, but I could set up a value for the thing I'm trying to find the cube root of, and then just run a for loop, because I know that the cube root has to be less than cube itself, at least for positive integers, things greater than 1. So I can simply use range to generate all possible things I want to use as a guess, and then run a for loop, where I'll run this and simply say, again, check to see is guess cubed equal to cube. If it is, I'm done. Let's see what happens if we try that one out. So I've got a little simple version of that over here. I'm going to start off with cube equal to 8, and if I run it, it does the right thing. It says cube root of 8 is 2. Let's try 27. And if I run that, wow, it's great. Cube root of 27 is 3. This is working really well, okay? But suppose I now give it something different, like 28, and I run it. What happened? Well, it completed. I can check that over here if I go back to my process. I've got things here, but it didn't print anything out. because I made a slip when I wrote the code. That code is going to run through all possible options for guess, but it's only going to print something out if, in fact, I find something that is the cube root, if there is a perfect cube. 28, that's not going to happen. It didn't give me anything informative. So I ought to clean that up, and I can, by simply saying, do the same thing. I've actually cleaned it up to add in abs here so that I'm going to deal with the negative cases, but do the check here, and if I get to a place where I've gone too far, simply break out of it, okay? Otherwise, run through the loop, but now, when I do the check, do the print. Otherwise, do the check with the second piece. And actually, I've done that in an inverse way. Here, I'm checking to see it's not a perfect cube, and I'm going to print that out. If it is a perfect cube, I'm going to basically determine whether I want the positive or negative version of it. So I'm cleaning up two things here. I'm allowing for negative integers, but I'm also allowing for it to print out something that's going to do the right thing. And let me show you what would happen if I run that version. So now when I run this, cube root of minus 27 is minus 3. And if I give it a minus 28, it says it's not a perfect cube, and I'm all set. What was my point? When I run the code, I shouldn't just run it on things I'm expecting, like perfect cubes. I should run it on other things to see if it does the right thing. When it didn't, I wanted to add in a different check. And I added in a second thing here, which I had done earlier, which is to make sure I can deal with negative integers and not just positive integers. But that now gives us a nice tool. I've got exhaustive enumeration, guess and check methods that can work on problems where there's a finite number of choices. I can come up with a way of exhaustively testing all of those, and it's a good way to generate guesses in an organized manner using those iterative loops as a technique to tell when I'm done and to return a great answer. And we're going to build on that idea as we move on.